So if you recall, what we had covered last time were some of the bare bones functional features. These include things like the lambda expressions and method references. You'll get a lot of experience programming with those throughout the course, a little bit in assignment 1B and a lot more in all the other assignments. What we're going to do now is we're going to talk about functional interfaces, and I'll give you lots and lots of examples of them. You will also see those all over the place in the class as we go forward in the assignments. So I'll first explain what a functional interface is in general, and then I'll also talk about some of the key functional interfaces, and there are really 5 of them that you see most of the time. These functional interfaces, lambda expressions, method references, and so on are the core functional programming infrastructure for Java and Java 8, and that all forms the basis for the concurrency and parallelism frameworks we're going to be focusing on the rest of the class. I'll give you lots of examples. All of these examples are available in my Java 8 folder, which you can see here. We'll also show how to apply these things to some interesting example programs, and all the example programs showcase various classes and methods that are defined as part of the Java collections framework, which you should be familiar with at this point, at least a little bit in terms of common collections like hash map and array list and so on, which you're getting some experience using. So let's talk about functional interfaces. A functional interface is an interface that can contain only one abstract method. You've already encountered this probably if you've done much Java programming in the form of things like the runnable interface, which has a single method run, or the callable interface, which has a single method call. So there's just one and only one abstract method. The functional interface is the type, or a functional interface is the type that's used for a parameter when a lambda expression or a method reference is passed as an argument to a method. So let's take a look at an example here. And this example comes from the EX16 folder in my Java 8 repository. And this is a very fun little example that's doing a bunch of different factorial computations. Some of them are sequential, some of them are in parallel, some of them use long, some of them use big integers, and so on and so forth. And one of the things I do here is just for fun, I have a little test driver function that checks to see how long any given implementation takes to run. So it's a way to get an apples-to-apples comparison between different implementations of factorial. And if you run the program, you'll see it's surprisingly different in terms of how these things behave. But here's the run test method. What we're doing is we're going to record and print the time taken to compute the nth factorial for some factorial, so for some n. And what we're doing is we're going to pass in a parameter. This is what's called behavioral parameterization. We're going to pass in a function that will be parameterizable relative to whatever factorial implementation we're trying to do. So we pass in this behavioral parameterized object, and we record the start time, and then we say fact.apply, passing in whatever n is, and then however long that takes, we'll record that and print the result. Now, the cool thing about this is this allows us to be able to pass in these different implementations without changing the run test function. So it's a great example of behavioral parameterization. And you can see we could pass in a parallel stream factorial, we could pass in a sequential stream factorial, and there's a bunch of other examples that I have there as well. Just for kicks, let's take a look at what the parallel stream factorial looks like. We'll cover this in more detail. This is kind of a teaser for what we'll do later in the course, but this just gives you a sense of kind of the basic idea. So what happens here is we have a factorial method that's static, so it's defined as part of some enclosing class. And as you can see, it takes a big integer n, and it returns a big integer. As you may recall, big integers can be arbitrary precision values that can grow to really anything, really large numbers. And what we do here is we go ahead and we go from, we generate a stream of values of longs from 1 to n, and then in parallel, we convert each of these longs into a big integer using the value of method reference. And then we go ahead and do what's called a reduction. We'll talk more about what reductions are later. But basically what we do is we give the reduction an initial value of 1, And then we go through and we multiply each pair of big integers together in that range, kind of like a tree, until we end up with a single reduced result, which will be the factorial. And it turns out if you run this program that if n becomes very large, then the parallel version is actually a win. If n is very small, then actually the parallel version is slower than the sequential version, which may seem a bit counterintuitive, but that's one of the characteristics of parallel processing. If you don't have a large enough number of elements to work on, and the amount of time you spend on each one isn't large, then the effort required to set up the parallel computation and merge the results together at the end can actually be more than the speed up from parallelism. So we'll talk a lot more about that when we get further into parallel processing. There are many different types of functional interfaces defined in Java 8 and beyond. And the reason why there's so many of them is that Java differentiates between reference types and so-called primitive types. So reference types are the types that you would expect if you're defining user-defined types. So things like whatever you need to do where you're going to have some generic parameters. And you can see a lot of things in here like consumer and function and so on. And these are things that require essentially arbitrary types as long as they're reference types. There are also primitive types, so things like longs and ints and doubles and so on. And Java distinguishes between primitive types and reference types. It's kind of annoying, quite frankly. Other languages like C++ don't make those distinctions. And the reason why there's all this support for primitive types is to support something called auto-boxing overhead elimination. And if you don't use these kind of specialized versions, you end up with auto-boxing overhead. And you can read more about the heartbreak of auto-boxing and the overhead here at this link. So one of the consequences is there's an explosion of functional interfaces in Java. We're going to focus right now largely on the ones that work on reference types, but be aware that for every reference type, there's also specializations of those reference type interfaces for functional interfaces for the primitive types like longs and ints and doubles and so on. As a general rule, you're well advised to learn how to use the built-in functional interfaces that come out of the box with Java 8 and beyond before you start to make your own. You could, of course, make your own, and there are times when it makes sense to make your own, and I'll show you some examples of situations where it makes sense to make your own interfaces, but as much as possible, you should try to use the ones that are already there because that's what other programmers would expect to see. So we're going to focus on the 5 most common types of functional interfaces: predicates, functions, bifunctions, suppliers, and consumers. There are gobs more of them, but these are the ones that you're going to see most likely when you start using the more advanced types of mechanisms in Java, things like the Java Streams package. Another thing to note, and I'll just mention this briefly, and then as we go through the examples, you'll get a better sense. All of the different types of functional interfaces we cover in the rest of the lessons for this part of the course are all stateless. Remember we talked before about functional programming wanting stateless operations in order to avoid dealing with side effects. So everything we're going to do here is going to be stateless, and that's a good habit to get into. And all the stuff you'll write for this class will also be stateless.